So the topic is enabling smart field boosting rice phenology estimation using airborne multispectral remote sensing data. Let's have an overview of agriculture. Uh, the disruptive activities on this planet has been changing our friendly relationship with our nature since more than 10,000 years ago, when the human beings are just gatherers and hunters, till today when they are hunters, when they are consumers and producers. We have domesticated several crops, expanding our cropland area to be around 11% of our global land area. We are expanding our technology agriculture sector together with our technology sector. But recently, some studies are showing that the productivity of our cropland areas and sustainability of our cropland area is decreasing. So due to some common factors like climate change, biodiversity, economic recession, etc. So how do we cope up with these challenges? Let's further have a look on the urbanization problem. We all have known that agricultural revolution has revolutionized after industrial revolution, but still with a growing, exponentially growing population size, the agriculture sector has to produce the food on the less farm area and with the less water problem. So how in this digital age, when we have access to drones, image sensors, GPS sensor robotics, and latest AI techniques, how we are going to enable our farmers to use this technology and to enhance our crop yield, enhance our crop yield to make the crops more resilient to the climate change and to make them more enhance our yield and to make the expenditures more less. So for this, we are using airborne remote sensing data for precision agriculture. So basically, the precision agriculture generates the detailed insight about the farms, so that our farmers and decision makers can make effective decisions and timely decisions that will optimize the yield while keeping the expenses and the chances of crop failure minimum. So basically, what is remote sensing? Remote sensing is the process of detecting and monitoring the physical characteristics of an object by measuring its reflected solar radiance. There are different platforms available for remote sensing. Handheld sensors, basically you have some sort of device that can measure some values, for example, temperature sensors and device sensor. You just scan the area and it gives you values, and then you process those values. Similarly, you have airborne platforms. Airborne platforms, you have like aerial vehicles, manned or unmanned. These aerial vehicles scan from area with the help of some sensors. You can capture the data and then process it for your application. Similarly, you have spaceborne platform. Spaceborne platform is basically uses satellites and its sensors to capture the relevant data, and then we process it, and it depends only on it depends totally on your application. We are using airborne remote sensing, and the mostly sensor used in unmanned aerial vehicle is these sensors: visual sensors, thermal sensors, LiDAR sensors, multispectral and hyperspectral. And depending on your application, you choose your sensors. For example, in agriculture sector, we mostly use multispectral and hyperspectral sensors because they can capture the vegetation indices more and monitor the plant health. We are using multispectral sensor. So basically, what multispectral sensor captures is we have the electromagnetic spectrum that captures the visible light, infrared light, and many more other bands. And the multispectral sensor captures the wavelengths in the infrared region. So basically, you can have the infrared band, NIR band, which we call, or you can have the red edge band. Red edge band is basically the transition area between the red band and the infrared band. So why we are specifically using multispectral sensor? Why we are not going towards RGB sensor? Because you can capture the area with an RGB sensor. You can monitor with overlaying your pictures. You can monitor the crop growth stages during these with the help of RGB sensor also. But our main goal is to capture the phenological stages of the crop. So basically, the NIR band is every crop growth stage has its associated reflectance with the NIR band. the RGB, the reflectance of RGB band cannot be differentiated in these growth stages, while the reflectance of NIR band, the difference of the NIR band is basically more than these bands. That's why we are using NIR band. With the help of this NIR band, we can calculate the vegetation indices also. Basically, this NDVI indices characterizes the chlorophyll content of the graph. In the here you can see that when the chlorophyll content increases, the NIR reflectance also increases. That's why the NDVI we get the NDVI values. We observe the kind of these NDVI values like this. So after covering the major terms associated with our project, now coming towards the agriculture remote sensing trend in Pakistan. Pakistan is famous for its agriculture land. It's around 47.4% of its area. It has the famous crop seasons, winter and monsoon, also known as Rabi and Kharif season. Besides this, what are the challenges with the remote sensing data is we have the average farm size of 5.2 acres. The fields here are very narrow. So the area is 5.2 acres, and for most of the region, the area is far more less than this. Secondly, we don't have the any freely available data for our region. So basically, we have to first select. We have to first select our area, and then we have to collect the data set for our area for further computations. So our main objective was to monitor. We have selected the rice fields for our research. We have selected an area with, I think, around 3 to 4 fields. We will monitor the whole growth period of the rice field and measure its phenological stages. And with the help of these phenological stages, we are going to train some model, or we will going to design some model, time series data, or some AI-based model to predict the yield. And with the help of that model, we are also going to enable smart field boosting in Pakistan. Basically, the rice crop has these growth stages. Basically, these are the stages of any crop growth: vegetation, reproductive, and ripening. But under these categories, we also have sub-stages like in rice, we have transplanting, tillering, panicle, initiation, flowering, and harvesting. These right now we are not modeling these sub-stages. Rather than this, we are modeling vegetation stage, flowering stage, and harvesting stage with the available data. So basically, our methodology is we will first acquire our data, then we process it, rectify it, create mosaics, and then we have to do some analysis like NDVI comparison, map the growth stages of the rice field. Going towards data collection, we have selected southern Punjab area, particularly in the Pushab region. We have total area covered around 8 acres. We have luckily we found three variants of the rice there. We have Kainat, Hybrid, and Super Karnal. Kainat is very famous under the name of Super Basmati rice. Hybrid is the newly introduced variant, while Super Karnal has been introduced a while ago. We have 2 hybrid fields around 2 acres. This yellow fields is showing hybrid field. The left side to the hybrid is Kainat field, and across the road is the Super Karnal field. We total area covered is 8 acres. Data collection has been done using Centra single precision NDVI sensor. It gives us red band, green band, and NIR band. And the drone uses Phantom 4. The speed of the drone is 6 to 17 meter per second, and the altitude is like 50%. And at 50 feet altitude, we have designed our mission for set. The overlapping area is 85% overlapping area. Basically these 3 variants, hybrid, Kainat, and Super Karnal. The planting period is different for each variant. The hybrid is planted around 2 weeks before Kainat, and Super Karnal is planted after 3 to 4 weeks of Kainat. So basically, the planting period and the harvesting period of these variants are different in each. This picture shows the data collection process we have done on 25th June. I don't know if it's visible or not. सर ये वाली लाइट ऑफ हो सकती है on 25th of June. It's not visible here, but we do not have anything. We cannot visualize or we cannot see anything on the 25th of June. But on 6th of June, when the panicle starts initiating, we see some shady areas on this images, and on 19th of July, after around 1 month, 1.5 months of planting, we see the shady regions has been increased. The density of the shady region has been increased. That is due to the tillering stage. This is the video of data collection process. This is the hybrid field. You can clearly see the panicles has started initiated. This is the kainat field. It is in the planting period. It's like the paddy state. Across this road, we have that superkernel field. This one is superkernel area. These both fields are hybrid, and this is kainat area. You can clearly see that the panicle has started initiated in this hybrid field, while the kainat is still paddy field. While the kainat is still in the planting state. So for data processing, once we have collected our data, what we do is we have the samples of the field. What we do is we create the mosaic of the whole field. We have used Pix4D Mapper for this. We just upload our pictures, and then you rectified it according to the embedded location. And we have these 467 samples, around 467 samples of the kainat field. It results in this ortho mosaic. This is the kainat field area. We have to mark this boundary region because there is an 85% overlapping of our field. So in these on the edges, it covers the area that do not belong to the field. So basically, we have to cover these. So we have to cut this area to calculate our original NDVI value. This is the NDVI value. This green region shows that there are trees there. That's why it's like green. And this is our original field. And it's in the, I think, starting phase around panicle initiation phase. And you can clearly see the difference that when there are trees, it's like more green, and it's in the around 0.4 to 0.2 range value. That's why it's like orange color. Once we have computed the reflectance map, we have to compute the average NDVI values for each field. We are not working with the chunks of the field, rather than we are here computing the overall NDVI field of our, in the overall average NDVI of our field. We will next fit the cubic supply. To basically, we have just samples around every 2 weeks. So we will fit the data. So we will fit the supply to interpolate the values between those 2 weeks. When we map these NDVI values, we have to calculate the change in the graph to mark our stages. So for this, we will using derivatives to characterize the change in the values. For this, we have when the derivative, we all know that the derivative, when it's increasing, the derivative value is positive, and when our graph reaches the maximum value, derivatives become 0, and then it starts decreasing. And at the end of the season, it will be like most negative value. So with this, we have a positive derivative. We will mark the start of the season, and the point where the derivatives become 0, we will mark it as a peak of the season. And it's also can be seen that the peak of the season is the flowering stage. Start of the season is the vegetative stage, and the end of the season where the derivatives becomes most negative is the harvesting stage. So basically, we have marked these 3 stages. This is the NDVI trend for kainat. This is the NDVI value. This is the differentiation, and you have seen that this is the start of the vegetative phase. The derivative is maximum, and then this is the decline in the decline in the derivative value, and where it is crossing that axis is the peak of the season. That is where your NDVI has reached the maximum value. Similarly, we have also mapped this for a hybrid state. We have performed the similar calculations, marked the start of the season, peak of the season. We have collected the data till mid of September. You can clearly see the trend in these NDVI values. This is the average NDVI value for hybrid, and this is for kainat. And for reference, I've used this from some reputed paper, this NDVI temporal profile. The NDVI temporal profile for rice is basically, it starts increasing after the vegetative phase, and then it reaches the maximum value during the flowering stage, and then it starts decreasing. You can map this on this hybrid phase. It starts during the vegetative state. It is like 0.04, and then it starts increasing, and then it reaches to the 0.77 on the end of August. That is the basically flowering stage. After that, the NDVI value starts to decrease. And I think it has been harvested in the in the end of September, it has been harvested. Its NDVS values at that point, I think it's around 0.2. Similarly, for Kainat, we don't have these values because Kainat is planted around 3 weeks later than hybrid. So that's why the whole growth stage period is shifted around 3 to 4 weeks. We have the maximum NDVI value on mid of September, and it is going to be harvested in the end of October. We have the rice season is going to be an end, and most of the data has been made available. So after computing the average NDVI's values and seeing this trend, we can clearly see that we can train our model to model the phenological relationship with these growth stages and to predict the yield. And for smart yield boosting, what we are going to do is we will use those NDVI information, that's phenological information, and we are going to predict the precise growth period of each of the rice, like the timeline of exact period, and then we are going to suggest whether it needs fertilizers or water to enhance its yield. And secondly, we have different variants available like Kainat, hybrid, and super kernel. We are going to see the growth pattern of these variants to exactly how these growth stages differ from one another and how it impacts on the yield. And that's the end of the presentation. Any questions?
So this increase of NDVI, is that a function of the amount of plants that is in that area, or is that a function of the plant itself? So does the individual leaves increase their NDVI, or is the NDVI just higher because more of the area of the region of interest is occupied by plants instead of soil?
So it's like you have, let me go back to these slides. It's like when you plant a seed, it's like initially after 20 days, it looks like this. The height is very minimum, and then suddenly the height, and after 20 to 30 days, it starts increasing. Its tillers started to form, and then this is the maximum panicle. This is the maximum tilleration after 20 days, and then panicle starts initiation. So what is panicle initiation? Its panicle initiation is basically you can call it the leaves. The leaf starts forming and it starts losing itself. So the area of that crop, the area of that seed, the particular seed, for example, there's one seed, the area starts increasing, the green area starts increasing. It's not like the amount of the plants here. You have planted the seeds, and then the area of each seed starts increasing. And that's why you see here you cannot, basically NDVI measures chlorophyll content. So here the chlorophyll content is minimum, and suddenly when you see that the leaf starts losing itself, then the chlorophyll content is maximum. That's why you have the most value in this flowering stage. And then the color of these, after flowering stage, the color starts decreasing. It's becoming more brown or yellowish. You can see that here. I don't know whether you can see it or not, but here it's like yellowish or brownish color. So that it cannot measure the chlorophyll content now, and especially the reflectance of NIR in this region is very minimal. Just like RGB band, that's why the NDVI value is very low. So it characterizes the whole NDVI signature.
If you would use this compared to what farmers in former days were expected, also good for the field that said, oh, now I can start to harvest my rice. What is really the benefit now? What is coming out if you have now a more precise measurement when you should more or less harvest, or in the past where they are roughly maybe based on experience?
So specifically what is the benefit is when they go and visit fields, if the field is very small, then obviously they can go and check whether it has reached to the harvesting stage or not. But in the where you have more area, like more than 5.2 acres, they cannot check each individual plants. They will just go with their intuition. So maybe there are some regions that for example, during disease attack, they cannot check each and individual area. They just go with their intuition and with their experience, and they spray the fertilizers. And some area do not need fertilizers, while other area does require fertilizers. So basically, the main our goal is, after modeling this, we are going with the smart yield boosting, and the purpose for specifically the smart yield boosting is we are going to predict that this area requires fertilizers, or this area requires water, and this area is not. This is going to enhance the yield. So I think we have to educate our farmers. We have to make them realize that it is going to benefit them.
But what do you expect at the end? When you just have more production, or what is really the output at the end?
Sorry, sir, can you repeat
So
it?
the output, what do you get more? So you said we look for seasons, we look for water is missing. We know when we should start harvesting in a much better way as before. But what do you expect at the end? All the things done by a smart farmer, what is the benefit for this coming out? Do you have any estimation compared to the state what we have now, where we more or less have no sensor system which track the fields and so on?
So basically, one of the basic idea we have is we are going to enhance our yield. Recently, the farmers here in Pakistan, they are usually going with the traditional method. They do not using the other, just like we have introduced the hybrid variant here. They are use their previous methods. We are going to this. We are going to compare the growth patterns of different variants also. So it can also help the genetic engineers. They can visualize that they have the stats that this growth stage or this type of genetic variant is producing more yield. So basically, it's all about producing more yield, because this is the cash crop of Pakistan. We want to enhance our revenue. We want to boost our revenue.
Yeah, I understand all these things, but we have no numbers. What do you expect to get more out?
Sorry, sir.
So the question is, if you use all the new technology, what we are not doing today, and you do it in a perfect way, or the farmer does it in a perfect way, how many, really for this cash cow, how many, what is the benefit for us if I do this compared to today? We have a 50% higher production, 100%, 45%, and the effort is more or less more than what you get out at the end.
So right now we do not have exact figure. It's in the research phase. We have initiated, Dr. Mosam has initiated the idea. We are going to keep the track of these. Okay, how much yield we are going to get, and how much its revenue, how much our revenue has been increased. We are going to get these stats, and then we are going to implement these on the larger scale. Right now, we do not have any stats. It's in the research phase.
Maybe I can add on to the answer of. So the work you have done, maybe it's like the initial work which is required to train and to develop some sophisticated crop models. So in that, like, your work can help to develop good crop model or maybe more accurate crop model. So if you have an accurate crop model, then you can simulate the production related to each variety, and you can do fantastic research, and like you can do benefit to the society. So, but my question was a little bit different. If you know the sowing and harvesting dates of your wheat, why not use this growing degree days methodology to compute logical stages? So maybe you can record the temperatures at the field, and you can compute those growing degree days, and those growing degree days actually can also tell you about this different growth phases of the crop.
Okay, right now we have not, we have just collected our data. We have not defined our exact methodology, like we are going to use some AI-enabled model or some other time series model. Maybe for that we will use it, but we have not right now defined our next step, like which model we are going to use, because Right now, we are in the data collection process. We have collected the data, and for the rough estimations of the NDVI profile, for our knowledge, we have seen that how NDVI is varying and how we can use it. Maybe at some later stage, we will find out that this method works best. So maybe you can use it.
Your senses, do you record the temperature at the peak?
No, right now we do not.
Precipitation?
No. We can. I think these things are in the NARC area. We can always get this type of information from their department if further we need this information.
Because if you know the variety which has been sown at the field and you know the sowing date, so with the help of growing the date, maybe you can grow phases, and you don't need the sophisticated growth time over the field and like NDVI computation, and then you are also using this line method, which is like which can also be very like how did you smoothen this whole curve. So yeah, maybe you can do both things.
You can, yes, we can do both things, but it's not like we are just modeling the rice thing. We are modeling more crops. So like the scope of our project is more than this. So for that, from that point of view, we are using the NDVI profile.
How much you confidence into our estimation rice yield and production? How much you are confident have you calculated any significant of this model? Model.
Till now,
Yeah.
no, we have not calculated till. We will calculate once we will develop our model and develop the relationship with the phenological stage with the yield, then we are going to do stats with this. Till this stage, we have not calculated it.